So California has recently decided to spend $100 billion making trains so that people don't have to use airplanes. And we're going to use these trains to set up a nice example of a system of equations. And you see here, I've got one train full of politicians, and that's cruising south from San Francisco, and another train full of government lobbyists, and that's cruising north towards San Francisco. We're going to figure out how long it's going to take before these erupt into a fiery ball of ash and solve quite a few problems in the meantime. Now, the way I'm going to do this is setting up a system of equations. And what I mean by that is I'm going to have two equations because there's two trains. I'm going to define something called x, and x is distance south from San Francisco. Okay? And for the first train, let's keep this color-coded here. The first train right here is going to be x1. Okay, x1 equals, it's 60 miles south, and it's traveling at a speed of 150 miles an hour south. So let me convince you that this equation that I just wrote is true. And if you've taken physics, great, you already know this. But what this equation means is at time equals 0, right? What happens at time equals 0? Well, this just crosses off, that's 0. You're 60 miles south. Great, that's your starting point. And if you wait an hour, what's 150 times 1? Well, that's 150. So after an hour, you'll be 210 miles south of San Francisco. So it looks like this equation is working. And in the same way, I'm going to set up another equation for this train. And that one is going to be called x2, the position of the second train. That is 160 miles south of San Francisco. But it's traveling north. So it's not going plus something, it's going minus. Because its distance south is decreasing with time. At time 0, it's 160 miles south. But at time 1 hour, for example, okay, well, it would have run off into the ocean, which is also a happy ending. But it's traveling north, so this number is decreasing with time. This number right here. Okay. So what I want to do is I want to find the time down to a very small decimal, it looks like. This one's nearest tenth of a minute. Oh boy. So it wants a very precise measurement of exactly when these two trains are going to collide, presumably because we're taking a movie of it. So the way you do that is you say, okay, what happens when they collide? Well, that's when x1 equals x2. They're at the same location. So to do that, you just substitute these equations into each other. You say 60 plus 150t equals 160 minus 230t. And now look at what we've got here. This is pretty cool. There's no more position anymore. It's just t. And I can solve for t. I'm going to add some t's to each side. I'm going to say plus 230t and plus 230t to each side. And what does that give me? Well, I get 380t on this side equals 160. Don't forget the 60 over here. Let's get rid of that by subtracting 60 from each side. And what do we have here? I'm working through this, and I get 380t equals 100. So now one more step to go, and then the fireworks start. 380 over 380. That's going to cross out my 380s right here, and I get t equals 100 divided by 380. Okay. So I get t equals 0.2631557, and it goes on for quite a while. That many hours. That's how many hours I have to wait until the fireworks start. So as you look at your answers here, there's nothing like that. And the reason is, this is hours. And remember what it wanted. It wanted minutes. So it's not a big adjustment. We just have to say, okay, great, times 60, and that'll turn this into minutes. Okay, so times 60. And we get t equals 15.79 minutes, approximately. And it looks like that's right here, 15.8 minutes. So that's the way you can solve this thing. It's a useful example of physics. Set up one equation for one train, one equation for the other train, and the thing you're looking for is when they're at the same position. So you have to find the equation or you have to find a way to solve these by setting those x's equal to each other.